So completing the square is our fourth technique to help us solve a quadratic. Its main use is to get us to go from standard form to vertex form. Once we're in vertex form, we can graph it, we can solve it, we can do a lot of things. Vertex form we know is easier for certain reasons. So how it gets its name, completing the square, is from a mathematical kind of picture like this. So say we've got these three quadratics, and we don't know our C term here, our constant term. One thing that you should notice about the pattern is all of the x squareds do not have a coefficient in front, or they all have a 1 in front. So I have one of these x squareds. This one, I have two of these x, so I'm going to put one right here. And kind of with the namesake, I'm going to try to complete a square. So what do I have to add to finish out this white square? What do I need to do to complete a square? I need just one of these 1 blocks. So this first term right here, where these question marks should be, I should have the value of 1 to complete the square. If I continue this process, I now have 4 x's. So you can see I need to add in a few more of these squares like this. I need a 4 of these 1's. If I add in 2 more of these x's, giving me 6 x's total, our third term down here, I end up having to add in 5 more of these 1's to complete the square. So this one down here ends up being a 9. Now, I do not expect you guys to see much of what's going on. I hope you just see a pattern that this is a perfect square, 4 is a perfect square, 9 is a perfect square. So if I were to do this one more time, x squared plus 8x plus what would have to go here in the next pattern, it's going to be 16. What this is helping us do is each one of these has become a perfect square trinomial, meaning x squared plus 2x plus 1, if I were to factor this using our AC method, I need two numbers that multiply to 1 that add to 2. It factors down to this. X squared plus 6x plus 9, the third one we had on the other page. I need two numbers that multiply to 9 that add to 6, 3 and 3. It factors down to x plus 3 squared. The last one that we looked at on that last slide, two numbers that multiply to 16 that add to 8, 4 and 4, it simplifies down to x plus 4 quantity squared. The whole thing is we're trying to get this perfect square trinomial. So x plus 2 quantity squared, when we talked about this in our polynomial unit, this does not make x squared plus 4. No. X plus 2 quantity squared was x plus 2 times x plus 2, and we'd have to FOIL our answer out and get x squared plus 4x plus 4. These were our perfect square trinomials. We know standard form, ax squared plus bx plus c, vertex form. What completing the square does is it takes us from here to there. So why use vertex form? Things that we've talked about on other videos. Vertex form gives us the coordinates of the vertex without any effort, and it helps us solve for roots easier because the variable x only shows up once. So when we have standard form, you have to graph, factor, or use the formula. With vertex form, you can graph, or you can just straight up solve, like it's an equation. That's what makes it easier. Graphing is easier, usually but we can just straight up solve it. So we're going to skip that part of it. So converting into vertex form, this is the process. The first thing that has to be true, this leading coefficient has to be 1. Cannot be 2. It has to be 1. Meaning, we have to divide everything by 2, including the y over here. Once we have that, we take our middle term b. So in this case, whoops, it's not 2 anymore. Take the middle term 2x. We don't need the, and we divide it by 2 and we get 1. We get that result and we square it. We then take that result and we add it to both sides of the equation so everything remains equal. We can combine any like terms, we simplify, and we factor. We're going to practice many of those over the next couple of days. Let's start with this one. First thing, our leading coefficient is 1, we're good to go. What I do is I take my b term and I write it right over here, 6. I need to take half of 6, which gives me 3. So our first thing that we need is half of our middle term, 3. We then have to square it, 9. So this is half of b. This is half of b squared. Now that we have half of our b squared, we're going to add this number to both sides. So we're going to add 9, and we're going to add 9. The left-hand side becomes y plus, y plus 9, and the right-hand side becomes x squared plus 6x. But here's the thing that we're going to do. It's a little bit strange. We are not going to combine the like terms here. Plus 9 plus 1. Why we're not going to do that is because what we're trying to create right here is our perfect square trinomial. That perfect square trinomial can be factored, but the best part is we don't have to worry about using the AC method or anything like that. So we have the y plus 9 is equal to our perfect square trinomial when factored. It's going to be x plus whatever number you put right here, positive 3. To get it back into our vertex form, it needs to be y by itself, so we're just going to subtract 9 from both sides, and we get y equals x plus 3 quantity squared minus 8. We are now in vertex form. If we wanted to solve it, we're going to set y equal to 0. Seems kind of strange. We're going to add 8 back to this side. Square root both sides. Gives us positive or negative square root of 8 equals x plus 3. Subtract 3. Get negative 3 plus or minus the square root of 8 is equal to x. simplify our square root over here. Eight can be written as 4 times 2, so we get a negative 3 plus or minus 2 square root 2 is equal to x for our answer. Let's try another one. Again, check to make sure that our leading coefficient is 1, which it is. We're going to take half of the middle term, which is 8. We're going to square it, get 64. And that's the number we're going to add to both sides. So we're going to add it in such a way that we have a perfect square trinomial right here. That perfect square trinomial becomes x plus 8, whatever number you have right here, minus 9. We subtract 64. We get y is equal to x plus 8 quantity squared minus, was that 73? Why we have this step right here is we can graph it from this stage. If we wanted to solve it by hand, we set y equal to 0, or whatever we want the y value to happen to be, in this case 0. We'd add 73 back to the right hand side, square root, that gives us positive or negative square root of 73 is equal to x plus 8. Subtract 8 from both sides, you get negative 8 plus or minus the square root of 73 equals x. We're going to double check to see if this can be simplified. 1 doesn't work for 9, 16, 25, 36, 49, 64. Nope, it's not simplifiable, so our final answer is negative 8 plus or minus the square root of 73, all equal to x. Maybe think, why is it always plus 8 in the middle? Well, it's plus 8 because it's a plus 16. We have a problem where there's a minus. Well, what's half of negative 8? Negative 4. Negative 4 squared is a positive 16. So we're going to add 16 to both sides. Like this. Why we have to add it to both sides is so we keep our equation equal. It's the same as solving. Anything you do to one side has to be done to the other, otherwise you are no longer working with the same problem. We now have our perfect square trinomial right here. Instead of it being plus 4 in the middle, it's now minus 4 in the middle, whatever number you have right here, minus 10. We subtract the 16, and we get x minus 4 quantity squared equals negative, not negative 16, negative 26. All this for completing the square. Again, we get it to this stage, so we have the option to graph it. If we wanted to solve it, we'd set it equal to 0. And go from here. Add the 26 back to the left-hand side. Square root. So get plus or minus the square root of 26 is equal to x minus 4. Add the 4, so we get 4 plus or minus the square root of 26 equal to x. We check to see if 26 is simplifiable. It is not. we have our final answer. Even if the number in the middle is rather large, it still approaches the same. Make sure there's 1 in front of the x. Half of our b term is negative 12. Negative 12 squared is positive 144. We get y plus 144 is equal to x squared minus 24x plus 144 plus 5. Here's our perfect square trinomial. It is once again a minus 12 squared plus 5. Bring the 144 over. Negative 139. We now have it in graphing form if we wish to graph. And if we want to solve it, we set y equal to 0. Again, we could set y equal to whatever number we want. It all depends on what 2 answers we're looking for. I want to draw a picture for, that was a very great vertical line right there. Let's try again, just make it a little more believable. So you have your parabola. Usually we want to find the roots, so why we set y equal to 0 is on the x-axis, the y-coordinate is 0. If you wanted to know the answer for when will the parabola have the y values of 5, 2 locations again, instead of equal to 0, you set equal to 5, and we solve it that way. You could solve it for any value that you want. If you decide that, hey, I want to know when it has a y value of negative 100, in this case, it doesn't cross, you'd have no possible answers for when it equals negative 100. And you'd see that over here in the work. We add that, so we get 139 is equal to x minus 12 quantity squared, square root. We get positive or negative square root of 139, which is equal to x minus 12. I have to add the 12, so I get 12 plus or minus the square root of 139 equal to x. Now we have to double check to see if 139 is simplifiable. 4 doesn't, so if I go through, 1 does work all the time. I know I said on the other page 1 doesn't work, but 1 doesn't really matter. 4, 9, 16, 25, 36, 49, 64, 81, 100. Pretty sure none of these work. 49 is the only one that I'm not 100%. I don't think it's going to, but yep, not even close. 139 divided by, maybe 36. Nope. 139 divided by 16. Didn't think so. This one right here. So none of our perfect squares work. I know 9 doesn't. I know 4 doesn't. So it's simplified right there.